So welcome to Organic Chemistry, Part 2, the functional groups. This is my third installment of Organic Chemistry, so let's get started. All right, talking about the functional groups. As we've been talking about in Organic Chemistry, I always say structure is king. So functional groups are essentially a certain type of structure, okay, that because it's a unique structure on a hydrocarbon, it gives it unique properties, right? It's a functional group. It's a certain type of arrangement that of carbons, oxygens, nitrogens on a hydrocarbon chain in a certain arrangement, certain what? Certain three-dimensional structure that gives it a unique function. We talk about biochemistry and biology, okay? Form and function. You hear that a lot with proteins. Well, proteins are nothing more than organic molecules, right? Amino acids have hydrocarbons with a nitrogen and a carbon. If you remember, double bonded to an O at certain. So in this slide, I'm just naming some of the functional groups we're going to go over. All right. And so again, we're just talking about, these hydrocarbons that have a certain arrangement. And of course, some of the functional groups I've listed below here, okay, are halocarbons, alcohols, ethers, aldehydes, ketones, organic acids, okay? And there are more. So this is just the most common and most important ones and the ones that we'll see in this course. So let's continue on. Now, Table R is your friend in here. If you're part of the New York State Regents curriculum, you have this. If you're not, sorry, you have to memorize this. Okay, so any case, they kind of made it very easy to identify. And let me explain. So this is half of Table R. And so the class or the type of functional group is listed here, halocarbon. And we dealt with this, okay, in the second installment as we had fluoro, chloro, bromo, iodo type of compounds. Okay, these are halogens, and that's why they call halocarbons. And here's an example. So we've named this one already. 2-chloropropane, prop for 3 carbons, ane for single bonds between the 3 carbons, and hey, we have a chloro group on the second. Notice they put it in the middle here, and that's a little bit of a lie, right? That's really that chlorine is bonded to the second carbon, all right? So make sure that you understand that. So what they give you in Table R, and this is definitely your friend here, is they give you the type of compound, the functional group. So this tells you that an F is bonded to a hydrocarbon and a chlorine or a bromo. Notice you go to the alcohol, there's an OH group. Okay, now they give you the general formula. Let me explain that. The general formula, I always think of the R as the rest of the organic molecule, the rest of the hydrocarbon, no matter how many C's. And the X is what we're adding as the functional group. Now, it may be in this case one element, but it also could be a group of elements and in a certain arrangement. So an oxygen bonded to a hydrogen, and by the way, don't show the bond here, but it exists, is a hydroxyl group. It sounds like a hydroxide. It's not. Hydroxides actually slough off bases. They're ionic compounds and are bases. Here, this is not a base. This is a covalent bond, so this doesn't slough off as an OH minus. That's important to recognize there. But the bottom line is these X's, or this general formula, tells us we have the rest of an organic compound, and then we have this function or this form giving it a functional group. So notice here's the R, and if I wanted to draw here, I'm going to. Okay, so here is the R here. I can do this. And here is the R here. All right, and those are the rest of the organic molecule. And if I change my color, because I can, okay, this is the functional group here. And here's the functional group here. So that's how the general formula works. Very simple, but it reminds you. So it gives you the name, okay, of the compound based upon the type of functional group it has. And then it gives you an example of how to name it. Okay, so if you forget how to name it, it gives you that. All right, and that's your friend here. And so when we name the types of compounds, we're looking for that group or element that gives it a unique function because it has a different arrangement. Look at an ether. It has an O surrounded by what? 2 R's. Okay, so this is the rest of an organic compound. Notice there is that one. And then the R prime is the rest of another organic compound, and that's what's right here. Okay, and in the middle is the O. And look how they name the ether: methyl group. Okay, that's the first one. And then they name the next carbon group around the O, ethyl, and then they add the word ether. You don't have to memorize that. They give you an example. They won't always give you this example to name. Sometimes they do, but you have that there. So this is a really important friend in terms of identifying the class of compound based upon a certain arrangement, okay, on a hydrocarbon. Okay, these are not hydrocarbons. They're going to have some other chemical, okay, oxygen, okay, or nitrogens below in a certain arrangement, a certain function, a certain grouping that gives it unique properties. And so a halide or a halocarbon has different properties than an alcohol. Why? Because halides have these what? Halogens bonded. Alcohols have different properties because they have OH, and ethers have different properties because of this O in between. And so that's how it works. So different functional groups give them different functions because structure is king. Okay? And this is the rest of the table R. Notice we have some N's here, some amines. So you have nitrogens, oxygens, and how they bond, and some double bonded to this carbonyl carbon. Doesn't really matter, but again, just the general formula. This is the structure. This is the name. Here's an example of the compound with example how to name that. So let's continue on our journey. Okay, so any case, we started with halocarbons. We've done this already, but identifying halocarbons, we have this general formula, and we have a halogen bonded. And if you remember, we named their R first, or hey, it's a one carbon group. It doesn't have a double or triple, so this is a, go to table P, methane, and then we have a chlorine. So we have a chlorine only on one carbon, so it's a it's a chloro, okay, methane. We don't have to say one here because it only has one carbon. This is something we've already have done. Okay. All right. Yes, there's some more subliminal messages that will pop up here. All right. And again, we don't have to memorize this. We have this reminder here. Okay. Although their examples aren't always clear because, again, this chlorine is in here because it's on the second carbon. If the chlorine was bonded to the first or the last carbon, it would be at the end. Okay, so again, table R is your friend, and there's the general formula, there's the example. So halocarbons have a long list of uses, including solvents. Solvents dissolve organic compounds, and there's so many needed because there's so many organic compounds, as we've talked about in other lectures. Pesticides, refrigerants, that's a big one. We still use them. Fire resistant oils and grease, ingredients in bendable materials, adhesives, sealants. Think about all those things. Electrically insulated coatings, plasticizers, plastics. Okay, there's so many uses that we don't have other chemicals for. In recent years, we still use these as refrigerants because these liquids have very low boiling points. They're very good at absorbing energy. So if you've got a air conditioner in your car, air conditioner at home, generally speaking, they're filled with these types of halocarbons. Okay, and they used to also just be used as aerosols, meaning we used to fill a can up with these compounds, and under pressure this can would push out the product that we want. For instance, if you like hairspray, and I love hairspray with my hair, okay, we would push them. We would have a liquid that was a halocarbon that was under pressure, and when you pushed on the valve and released the pressure, it would push out, okay, the product, okay, under pressure. So because they were liquids, and they, under warm temperatures, they boiled easily, so they were used as aerosols. So growing up, there was a major problem with these aerosols. Although we still use them as refrigerants, okay, there had to be some regulations because growing up, my environmental problem in the 80s that I grew up with, as yours is global warming, is the hole in the ozone layer. Okay, and so if you didn't know, O3, okay, is in the troposphere, about I think 3 to 6 or 7 miles high in the air, is filled with all different types of gases, including O3. Now, O3 we've studied as this, it's an unstable molecule, even though it's stabilized a little bit because of resonance. We've definitely drew its resonance structure. Now, with radiation, and particularly UVB, and a little bit of UVC. These are the high energy ultraviolet light that we can't see that is cancer causing. And so what normally happens is the O3 absorbs this type of radiation, this photon of high energy, high frequency, small wavelength, and it splits into O2, which is a normal oxygen, and an oxygen radical. I say radical because this thing has 6 electrons, so it's highly reactive because it wants 2 more. And this highly reactive compound can now collide with O2 and reform O3 again. So what O3 can now absorb. So having O3 or ozone in our troposphere, okay, allows us to survive on land because it absorbs a lot of the UV radiation, not all of it, but a lot of it. So therefore we're hit less often with these high energy photons that come from the sun. It's a protective layer. We were worried about a hole, okay, or having less of it, therefore more of these UV radiations that could cause more skin cancers. Remember, skin cancer is the deadliest cancer, the most prevalent cancer that we actually have in society, okay, and it's due to these UV radiations. So we were worried about losing our ozone layer because we use so many unregulated compounds. We call them chlorofluorocarbons. Remember chloro from table R, and fluoro, and these are called CFCs, and there's a bunch of different types. Freon 22 is a common industry name for this one type of refrigerant that we still use, okay, in our air conditioners, okay, but these were used as aerosols. And what these guys will do, these chlorofluorocarbon CFCs, they will be released by the aerosols or released by a leak, and they'll get into our atmosphere. Now this HV is energy equals Planck's constant times the frequency of visible light. Okay, so visible light, a low energy photon from the sun, will cleave off one of these chlorines. Now, if you notice, this is a chlorine radical. And I say radical because chlorine likes to become Cl2. Chlorine has 7 valence electrons, and therefore it fills its octet by bonding with another chlorine. But when it's by itself, it just has 7, highly reactive. Okay, and you can see from mechanisms that this chlorine will what? Act as an intermediate in the next step and attack an O3. And when it attacks an O3, what can happen is it essentially cleaves the O3, becomes a ClO with oxygen. This ClO, okay, will react with another O3. Chlorine comes off. And guess what? It starts the process again. Chlorine can now attack another oxygen. So one chlorine coming off, and it's easily cleaved by visible light in the troposphere, okay, will act as a catalyst that's not consumed and keep catalyzing the decomposition of O3. So you don't need a lot of these in the atmosphere for them to produce a lot of destruction or breakdown of the O3. And we were worried about having holes and depleted ozones that would cause everyone to walk out of their homes and have cancers. And there never really was a hole, but we were definitely depleting it. And so international regulations came into effect and really prevented a lot of these holes or this depletion. But we still use them, and they still escape in our environment, and they're still doing that. Okay, but so CFCs, really important part of the history of environmental problems growing up. That was the major one there. You should be aware of that. Okay, so on to some example of other halocarbons in our environment. So here's a dust-off chemical. Okay, and the dust-off chemical uses this very inert chemical. Why is it inert? It's not a CFC, but it's pretty inert because it's got these fluorines that bond pretty strongly with the carbon. How would I name these? Well, how many fluoros do we have? 4 of them. So this would be a tetrafluoro, but what carbons are there on? Would this be 2, 2, 2, 1 or 1, 2, 2? Well, lowest number possible. So 1, 1, 1, 2 tetrafluoro, F for 2 carbons and an ane. You can see how that works there. Okay. Now, I'm not expecting you to name this one, but this is an important, another environmentally disastrous chemical that we used. Okay, this chemical here is called for short DDT. My dad was a farmer in Riverhead, and he used DDT. And give you the reason why he used it. He didn't know the environmental impact was as agriculture took off in Long Island and people were growing more and more potatoes. And the reason why they're growing more and more potatoes is because they were making money growing potatoes. And Long Island had a unique at the time, you didn't have a lot of different varieties of potatoes. So Long Island had a very warmer climate compared to, um, let's say, Connecticut or New England. And so Long Island served the surrounding states with potatoes, okay, and had a great environment and had a little bit longer growing season. And they could actually grow them a little earlier because of the warmer climate of having water surrounding the island. Okay, but the problem is as people grew more and more potatoes, there were breeding grounds for more and more um, potato insects, and so they had to start using insecticides. And so my dad was always telling me the story when the Colorado potato beetle first landed. I don't know if it was the 50s or the 60s, but it decimated crops, and farmers were starving, and until they started using these pesticides, and they didn't know at the time, but every year they needed a new insecticide. And of course now we know what happens is because of natural selection. Okay, um, basically there was these potato beetles getting more resistance. So really interesting. They needed to use a brand new insecticide every year until they got to DDT. That worked every year because it killed the potato beetles. It was just deadly to the potato beetles, but it got into the food chain. Those birds who ate the potato beetles, they got that into their food chain. And of course, the predators on top of the food chain were affected. And so, if you didn't already know, there was a time when the bald eagle, our national bird, our national animal, I guess, okay, our symbol of our freedom, the bald eagle, was borderline extinct. It was endangered to the point where it might have gone extinct. There was only a few nests left in the United States because DDT got into their system and it affected the way they laid eggs. They couldn't lay an egg that was firm enough. Therefore, the eggs came out half broken and their offspring died. So we had to stop the use of this chemical. And eventually, these guys were not endangered anymore. And now, in certain parts of our country, these guys are they're almost pests for those people that live in areas where there's bald eagles. They're almost as a nuisance as, let's say, our seagulls. Okay, and it's very interesting in different parts of the world or different parts of the country, like Alaska. These guys are like scavengers, and they go into your garbage, and you don't think of that as a bald eagle here, but they made a comeback because we did what we stopped the use of this DDT. Okay, and it's called DDT because it's dichloro. There's your two chloros. Diphenyl. The phenols are these benzene rings. Trichloroethane. Ethane is because of the what? 1,2 carbon that's bonded here. C here, C here. Remember, these are cyclohexanes with alternating double and single bonds. So just another naming system. I'll never make you do that for a test, but some background you should know. All right, so on to alcohols. All right, alcohols are the functional group ROH. They basically have them, and now we've already named halocarbons. So now, how do we name an alcohol? Well, the same thing is here. What we do is we find the longest continuous chain of carbons that never changes. 1, 2, 3. So that's a prop. Okay, that's right there. Now, because we can figure out because of the hydrogens. The hydrogens kind of tell us the bonds in between. We've been through this before. These are single bonds between the carbons. So this is propane. All right, we take the E away and we add OL for alcohols. But because it's an OH group, it can attach to different carbons. So this OH as written is on the end, and we always put the attaching group. So now it's an attaching group, just like a methyl, ethyl, or a Grodsky. Okay, it's on the first carbon. Yes, you could say 3-propanol, but that'd be wrong. Okay, because based on the IUPAC naming system, the substituent group has to be the lowest carbon. So this is 1-propane with an OL group. Take the E away and we have OL. And if you forget, table R is there to remind you. Okay, so here are some examples. 1, 2, 3, that's a prop. The OH group makes it an alcohol, so it's propanol, and it's on the first carbon, so that's 1-propanol. This is the exact same chemical formula. And by the way, this is an isomer, same exact molecular formula. Okay, but now this OH group is on the second carbon, so it'd be 2-propanol. And these have different properties. I've talked about this. This one you could drink, this one will kill you. Different properties because of a different three-dimensional structure. Although they're both alcohols, they'll do that. All right. Now, alcohols have some unique properties. They're flammable. Some of them can cause physiological effects in our bodies. Obviously, they're depressants. They slow us down. They make us sleepy. Okay. They affect our neurological system. Obviously, we'll talk about that. Now, so here's some other examples. Methyl alcohol is a common name, but we call it methane with an OH group is a methanol. We don't put a number there because it's just one carbon. Here is ethyl alcohol, a very common name also, but it's 2 carbons, and the OH group, okay, is on the first carbon. But because you could put this, you can flip this over, it's always on the first carbon. We don't put a number here as well. So this is ethane. Take the E away, add OL, and ethanol is the alcohol that's produced in anaerobic fermentation. Okay, and we'll talk about that in chemical reactions. So ethanol is made by fermenting, taking some kind of glucose, whether that's from wine, grapes. Grapes make the wine, or hops makes the beer, or grains. The sugars from grains can make, um, you know, your liquor. Okay, so in any case, phenyl is another word for the benzene ring. Okay, there's your cyclo compound, and that circle just means that you have alternating single double bonds, and don't worry about that. And then of course, here's an interesting one: ethylene glycol, very important, okay, compound that we add for different industry uses. This is an H here. 1,2 is your eth, single bond is ethane. Take the E away. Now because you have 2 OHs, they put a di here. But they put the di in front of the ending. The OL ending is for the alcohol from table R. So you got to put the di next to where it's the 2 of what? The 2 of the OL. So interesting, it's an ethane diol, and we need the numbers to say where they are, 1, 2. Okay, so interesting naming system there. All right, glycerol. Now that's another important organic or biochemistry compound. Glycerol with fatty acids make triglycerides, and that's how we actually store fats in our body. So we have a lot of this glycerol running around. But what's a glycerol? Glycerol is an alcohol. Here's your R and here's your 3. So how would you name glycerol based upon ethylene glycol? Well, 1, 2, 3. That's a prop. Single bonds between them, propane. Take the E away and you add OL, propanol. But we've got 3 of them. So it's propan triol, and we go, where are they located? Because they could be on the same carbon, right? 1, 2, 3, propan triol. Okay, propane, take the E away, add OL, but because there's 3 of them, we put the tri in front of the OL to say, hey, we're talking about 3 of the OH groups. Okay, and we need numbers for every substituent group. Again, if you forget, there's an example. So here's 1, 2, 3, 1 propanol. We've had this one, second OH group, 2 propanol. How about this one? I haven't given you this one yet, so try this one for size. Hope it fits. Well, 1, 2, 3, 4. Go to table P if you need to. So meth, eth, prop, bute, single bonds, butane. Take away the what? E? Add an OL. Table R is going to help you remind you that. And what carbon is it on? Is it on the 3rd or the 2nd? Always put the attaching group on the lowest number. So that's 2-butanol, or take the E away, butanol, right? How about this one? A little more advanced. You can pause this now and try this, or just wait with me. If you're not sure, always start with the longest continuous chain. 1, 2, 3, 1, 2, 3. So therefore, longest continuous chain is 3 carbons. They're single bonded. So table P is a prop for 3 carbons. Propane. All right. All right. And now I have a propane and propanol. Right. I have a propanol. And then I have a methyl group. And so I have 2-methyl, right, on the second carbon, 2-methyl, and then I have a 2-propanol. Remember, this is 2-propanol? So think about this 2-propanol here. I'm adding a methyl group in its space, so I need to say 2-methyl, 2-propanol. On the second carbon, there's a methyl group. There it is. Onto a 2-propanol. What's a 2-propanol? An OH group on a propane longest continuous chain that has single bonds. So you can see how that's done. And it's kind of a neat naming system. You don't need to come up with common names. Okay. All right. So aldehydes, next one. Now I call aldehydes an ending group. Okay. Sometimes I call them a cho mama group. And the reason why I call them the cho mama is so, okay, I won't get to doing mother jokes, but cho mama is CHO at the end. So sometimes they don't show the structure, they say a CHO, and that's kind of confusing because we know that a carbon can't bond to a hydrogen and then bond to an oxygen. Hydrogen's terminal, makes one bond, but they'll sometimes put CHO at the end for aldehydes. And really what that means is, here's your what? Your formula. Rest on organic molecule that can be some number of carbons and hydrogens, and then at the end you have a carbon double bonded to an O, so this is really double bonded to an O, and that's single bonded to the H. They really should write COH, but they always put CHO forever, so think about that. All right, you will get it, I'm sure. All right, so how is this different? Well, an aldehyde has an ending group. Because it's always at the end, we don't need a number to say where it's at. It's always at the first carbon, so we don't say that. Okay, if you were naming, this would take precedence, okay, for other things. In any case, it's a C double bonded to an O. It's called a carbonyl carbon, and to a single bonded H. All right, and how do we name it? Well, look at the example. 1, 2, 3 carbons. There's your prop. Single bonds between the carbon. Do not let this double bond confuse you. It's single bonds between the carbon. So that's prop. Okay, it's a propane. This does not change anything. The ane, ene, and ine are the bonds between carbon. And basically, if you think with me, carbon has 3 bonds to the H's, 1 to this carbon. This carbon is single bonded to this carbon. It's single bonded to this carbon, so it's got room for 2 H's. This carbon is single bond to this carbon, single bond to this H, and has 2 bonds to this O. Every carbon has 4. And we take the E away, and we add al for aldehyde, and we don't need a number. This is a formaldehyde. This is a compound we use to prevent the decay of organic molecules. So a lot of times you'll see samples dipped in formaldehyde to prevent the samples from decaying. Now you don't use the samples anymore, and this has been deemed a carcinogen, so you don't see this as much. But formaldehyde was a common name. But the IUPAC name, hey, what is this? 1 carbon, meth, methane. It's got the C double bonded OH ending, so methanal. All right, methane, take the E away, add al, because you've got this functional group that gives it its unique properties. This is meth F. Ethane, single bond. Don't look at this ethane between the carbons. Take the E away, and this would be ethanal. Don't need numbers. Okay, and how are aldehydes made? They're by oxidation of primary alcohols. Primary alcohols have OHs at the ending carbons. Now if you say, what are these lines right here, Mr. Grodsky? Well, these lines represent carbons, and they love to show the carbon backbone in organic molecules. Okay, so party people, they left out the H's, but here they're saying a carbon double bonded to an O. Bottom line is they left the H. Here's your aldehyde. Okay, so the only way this could be oxidized, okay, that means it lost some electrons, right? And so this gets oxidized and becomes an aldehyde. That's a really important reaction, okay, as we're going to talk about ketones in a second. All right, so there's my functional group, CHO-MAMA, CHO. It's at the end, and how we name this? Well, 1, 2, 3, longest continuous chain. That means I have a methyl group. And so on the second carbon, I've got a methyl. 2-methyl propane, take the E away, propanol. 2-methyl, propanal. Al, I meant al, for aldehyde. Okay, how about this one? 1, 2, 3, 4. Longest continuous chain is 4, not just because I'm reading across, because 1, 2, 3, 4. I'm sorry, this has to be the longest continuous chain because this is my aldehyde. Okay, and so 1, 2, 3, 4. So it's a butane, single bonds between the carbons. Take the E away, add al, butanal. On the second carbon, you have what? 2 methyl groups, 2,2-dimethyl butanal. Okay, and this one, 1, 2, 3, or is this part of the longest continuous chain? What do you think? 1, 2, 3. Is it a methyl? 1, 3 methyl propane? No, it's part of the longest continuous chain. This is not a methyl group. So 1, 2, 3, 4. Butane, single bonds between the carbons. And take the EUA and add al-butanal. It's not a methyl group. Longest continuous chain. All right. And look at here. Oh, what is this right here? Oh my God. Well, it's a chomama group. It's an aldehyde. Okay. And notice, all right, what we have here. We've got a double bond. We have some methyl groups. Okay. If you want to give that a try, you can. I'll give you. You could what? Pause me and give that a try. It's a lot of fun. But you've got an alkene here. All right. See what you can do with that. All right. I'm going to show you the answer. And here's what I got. 3,7-dimethyl, 6-octanol, octene. Now 6. You're going to say, Mr. Grodsky, how do I get 6 here? The chomama is an ending group, right? So it must be the first what? Carbon. It takes precedence. 1, 2, 3. There's your methyl. 4, 5. And there's your 6. That's where the double bond starts. So 6-octene. Take the EOA octanol, and then you have on the 7th the methyl group. That's not a Regents question, but a lot of fun. And you would say, I knew that the double bond takes precedence, but I didn't sure about, well, this has to be the first carbon. We're never going to put a number for an aldehyde. So that had to take precedence there, okay, as I did up here. And if you didn't get that, that's fine. If you did get that, congratulations. That's really, really an orgo naming system right there. Again, way beyond the Regents curriculum, but a lot of fun, okay, if you think about it. Moving on. All right. Cinnamon is really a famous aldehyde. There it is. These are carbons, right? And there's H's. This is your phenyl group or benzene ring. Here's a carbon double bonded, and there's your C double bonded to O to an H. So cinnamon's a really famous aldehyde, and it's called cinnamon aldehyde. Okay, so cool beans if beans are chilled, or if they're sprinkled with cinnamon, they're cinnamon beans. Sorry. Okay. Ketones. Okay, so I'll do ketones next. I might be going a little out of order to table R, but I think it makes sense. So a ketone, okay, is you have an R, which is what? Is, again, I'll show you that. We'll do some drawing here. All right, so we've got R, and this is the example of the R, the rest of an organic molecule. Then we have R prime, which is the other side of the organic molecule. So what you have, party people, is you have two sides, two different rests of organic molecules, and you have this carbon double bonded to an O in the middle. I love to talk about ketones as nothing more than aldehydes in the middle. They're not at the end. So this is a carbonyl carbon that's not at the end. There's no H here. Okay, that would make it a what? At the end, and that would make it an aldehyde. This is in the middle of a compound. So guess what? We're going to need a number. And as we were doing for the alcohols and the aldehydes, we have this own ending. So 1, 2, 3, 4, 5, longest continuous chain. So it's a pent. There's single bonds between the carbons based upon the hints of how many hydrogens. We've been through this. So it's a pentane. Take the E away and add own. And of course, we need the what? We need the number. Okay? We need the number. And why do we need the number? Because where is this carbon double bonded to the O? All right. And so it's 2-pentanone. And these are also very, very famous solvents. Okay. This is probably the most famous solvent, acetone, commonly known as nail polish remover. What would its IUPAC name? Acetone is a common name. Okay. And it helps dissolve a lot of different compounds that are polar and nonpolar. It's got a big cloud of electrons, and it's also got a polar carbonyl carbon here, okay, with the oxygen. Any case, naming this 1, 2, 3, meth, eth, prop, single bonds between the carbons. Don't get confused with this double bond to the O. That's the functional group, okay? So this is meth, eth, prop, propane. Take the EUA propanone, okay? Now, you could say 2-propanone, but to have a ketone, it must be in the middle. So you don't really have to say 2-propanone. There's no example of any other propanone, all right? How about this one? Give this one a whirl, all right? Name this one. Longest continuous chain rules still apply here. Okay, I got 5. So I've got a pentane, single bonds between the carbons. Take the E away, add one, pentanone. And on the third carbon, okay, no matter how I count my carbons, 3 pentanone. Okay, good stuff. All right, and there's my carbonyl group. There's my ketone. It's in the middle. Aldehydes at the end. Okay, ketones and aldehydes share the same carbonyl group and thus are made in similar fashion. They're both produced by the oxidation of alcohols. Now, primary alcohol is an OH group at the end. And because it's at the end, it makes an ending aldehyde. Now, if I've got a secondary alcohol, I got an OH in the middle of carbons. And that's going to give me a carbonyl carbon group in the middle. Okay? And by the way, this can be oxidized one more into an organic acid, which we're going to talk about. This stops. Okay? And that's why we'll talk, ethyl alcohols become aldehydes and eventually becomes acids, and that's why wine can become vinegar. Vinegar, of course, is an organic acid. Okay? So the synthesis, we oxidize a secondary alcohol, an alcohol in the middle. Okay? All right, moving on to ethers. I like to think of ethers on either side. Okay? On either side. All right? So here is an R. Here's my R, the rest of an organic molecule. R prime. Hey, it's on either side. Look at the example. They name the groups of carbons, okay, on either side of the compound. So this is a 1 carbon group. There's your methyl. Here's a 2 carbon group. There's your ethyl. Remember, we add YL for attaching groups. And then we use the word ether. Always put ether at the end. I always think of them as on either side of the single bonded O. So looky here. I've got 2 carbons on this side, which means that this is an ethyl group. Okay, and guess what? I got 2 carbons on this side. Same idea. It's another ethyl group. So guess what I call that? Diethyl ether. Okay. How about this one? I've got a methyl group and an ethyl group. So like you've seen up here, it's the same one. It's methyl, ethyl, ether. You're naming the carbon groups around either side and add the word ether. Again, you don't have to memorize this, party people. You can just use table R to help you remember how to name these. And these are made by alcohols coming together. Now honestly, the OH groups would hit each other. We talked about chemical reactions have to have what? Collide with the proper orientation. Well, this OH group would have to hit this OH group. Water comes out called dehydration synthesis, and they come together. Okay, so moving on. So look at the vanilla extract. Okay, and I probably talked about this in class. To get this oil, okay, from the vanilla root, third world countries will hire people, mostly children, okay, to bang on that root and get the oils out. Okay, and you pay a certain amount of money for that. And people say that vanilla that comes from this method tastes better than the imitation vanilla. Let me help you. The imitation vanilla you buy is the same chemical formula. The vanilla formula, whether it's made synthetically in a lab or pulled from the root, it's the same what? Formula. But people love to say I must have, I don't know, had child labor, okay, hammer out these oils on a hot sunny day to flavor my food than buy something cheaper that doesn't use that kind. But now I don't know if they use kids to do that, honestly. But people will talk about vanilla extract as tasting better. I don't know if it's a placebo or not, or are there other molecules that go with the vanilla that come from that. But in any case, getting it from the plant or the root of that plant is a lot more expensive. But the vanilla, okay, compound that gives the flavor is exactly the same imitation or coming from natural sources and a lot cheaper. But in any case, getting back to this, okay, if you look at this molecule, it's got a couple different functional groups. We have an OH group attached to what we say the rest of the organic molecule. So what would this OH group be? Okay, of course, that'd be the alcohol. And now, what about this right here? Okay, we have an organic molecule here, and then we have a rest of an organic molecule. So we have an O around two things. Now this second R prime here is big, but it doesn't matter. Okay, that'd be on either side. And then what do we have here? A CHO, chomama, or CO double bonded to an O, but at the end, and of course that's an aldehyde. So a vanilla molecule, whether you get it from the root or you get it synthetically made in the lab, okay, and you can argue it tastes better or whatever, it has 3 different functional groups on it. Kind of cool. All right. And then we're going to end up with organic acids, okay? And these are called the COO groups, COO, okay? And these are interesting because they're also an ending group. They're kind of like an aldehyde that has an alcohol at the end. So they're COOH ending. So you're going to see this very famous C-COO ending. Remember, aldehydes are chomama. These are COO. All right. Any case, how do we name them? Count the longest continuous chain. 1, 2, 3. That's a prop. These are single bonds between the carbons. Don't let that mess with you. So propane, take the E away, add oic acid. Okay, and again, oic acid. So look at here, methane with a C double bond O to an OH. This is an organic acid. This is methanoic acid. Now, for those that were in more advanced chemistry class, like AP chemistry, the reason why this is an organic acid is because this H, which has 2 electrons shared with this oxygen, these 2 electrons can move, and what they do is they drift toward this carbon because you have 2 oxygens here that are now attracting other people's electrons. Remember, electronegativity is the ability to attract other elements' electrons. So if you think with me for a second, okay, if you've got this O and you've got this H and you've got these pair of electrons. Remember, hydrogen brings 1 and oxygen has 6. Okay, that's why it makes 2 bonds. This pair of electrons will drift away from the H, okay, as it what? Is attracted to these electrons. And if they drift away, get pulled even farther, this H can leave without its electrons. We call that a proton or an H+. And acids, of course, increase the H+ ion concentration and therefore lower the pH. Another reasoning, if you want, okay, if you lose the H, what do we have here? We have a C double bonded to an O, and then we're going to have an O, and it's going to have 3 lone pairs, which makes it negative, and it's going to be bonded to something else. Well, who's to say this can't be single bonded? So this has resonance structures. And resonance structures, okay, allow for the oxygen, or I should say allow for this carboxylic acid to be more stable as a conjugate base. Meaning with the resonance structure, it makes it ability to be stabilized. It's not going to break down. So if something can exist without the H, then therefore it can lose its H. And if it can lose its H, it's an acid, okay? That's where I was going from. So if I had too much info there, sorry. How do we name this? Meth-eth. So ethane, lose the E and add oic acid, so ethanoic acid, which is also called vinegar. Now, where I'm from, or at least where I teach from, we call it vinagre, because that's how we do things in West Hampton Beach. Okay, so ethanoic acid. How about this one? 1, 2, 3. Also, we call it acetic acid because if you lose this H, COO negative, and then CH3 here is called the acetate ion. We've seen that before, okay, in our table F. Okay, but this one, 1, 2, 3, 4. How we name this one? Well, now careful, a little trick, okay? 1, 2, 3, 4, you would say butane, butanoic acid. Careful, this should be CH2 in the middle, CH2. Losing some H's here means there must be a double bond, party people, right? Don't forget, that's a little tricky. So we have this C, and we have 3 H's, and then we have a CH and another CH. We bond to this C, which is your carboxylic ending, carbon double bond to an O and then to an OH. Something's wrong here. Every carbon has 4 bonds except these 2, which means what? We must have a double bond there. So that changes things. 1, 2, 3, 4. That's butene. So we say butene. butanoic acid, right? So that's how that works. Okay, so that's going to be butanoic acid because of the double bond that exists here. It's butene, right? All right, beautiful. Okay, now how do we make organic acids? We take a primary alcohol, an alcohol that's bonded to one carbon or bonded to a carbon that's only bonded to one other carbon. Okay, it gets oxidized to an aldehyde. And of course, that gets further oxidized to carboxylic acid. So an ethanol molecule gets oxidized if you expose it to oxygen and eventually becomes vinegar. Okay, secondary alcohol can get stuck at a ketone, can't go any further. All right, so here are some naturally occurring organic acids. Now, organic acids are never going to be as strong as like hydrochloric acid or the strong acids that have Kas that are incredibly large. They're weak acids, but they're acids nonetheless. So this is a, look at this guy. Okay, so this guy has there's a Ku groups there. Okay, so actually this has 3 different Kas if you're in that part of it. There's an alcohol there as well. Cool beans. All right, and of course, really important, these are the only organic compounds that are electrolytes. In fact, they're the only covalently bonded compounds that are electrolytes. What are electrolytes? These are compounds in solution that will conduct electricity because of free ions. So because there is some dissociation, they're weak acids. All right, so organic acids are weak acids because they do not give off all of their H's. What I mean by that is if there's 10 of these molecules, maybe only 2 become the conjugate base that's negative and the H plus that comes off. So only 2 out of the 10 will do this. But they do it nonetheless, and they are acidic because they increase the H plus ion concentration. Now, we understand that bases can neutralize this. We should be aware that H pluses, okay, and hydroxides, remember our acid base work, will come together to make water, which is neutral. A positive and negative come together. And this is how we would neutralize this acids. Acids in high concentration are uncomfortable, okay, and can be deadly. Same thing with hydroxides. So we can neutralize them. All right, so the danger of acid and bases. But what they love to do with functional groups is try to confuse you with the idea that an alcohol can be a base. What's an alcohol? From table R, we know it's an R, the rest organic molecule, and an OH. And people think, because they're robots, OH is a base. It's not necessarily. If this is a carbon-based compound, and this is a covalent bond, and this oxygen covalent bonds with the O, this is not going to slough off. For instance, NaOH is a base. Why? Well, because it's an Na plus that's really attracted to a polyatomic ion. They may write it NaOH, but this is an OH minus. So it sticks together because of differences in charge. So this particle, OH minus, exists in this ionic form as a solid. And as a crystal, this Na plus will attach to this OH minus. And you should know that ionic compounds are nothing more than positives and negatives attracting each other. And this ionic compounds are solids. So these are naturally solid compounds that can be dissolved. When they're dissolved, they break apart into the free aqueous ions. Okay? So they dissociate into free ions in water, and therefore they're also electrolytes, acid bases, okay, and salts. So bases, for most part, are just an example of a special kind of salt that breaks apart. So this OH minus already exists in this compound. Same thing with this. So you see a metal and an OH, that's a base. But when you see a hydrocarbon here, okay, and an OH, that is not a base. Now, by the way, ammonia is a very important base, and that's a base listed in your table as well. So the only one that's not a base, okay, is the alcohols. Alcohols are not bases. They love to mess with you with that. So we're going to get rid of the drawings and see if the great Grodsky agrees, okay, if C is not a base. And he agrees because it's an alcohol. And this is where we're going to stop. Okay, and we'll pick this up on a minds. Please mind your own business until we get back to this. Hope this helped. See you next time.